Hello, this is a workthrough of NZQA Level 3 Calculus Examination 2025 91578 Applied Differentiation Methods in Solving Problems. So the first question is just a straightforward differentiation question. This is an application of the power rule. So we've got a function, it's a polynomial here, inside some brackets raised to the power of 5. So the power rule is if you've got a y equals x to the power of a, then when you differentiate it, you get ax to the power of a minus 1. You reduce the power by 1, and it's an application of the chain rule. If you've got a function, if you want to differentiate a function that's got a function inside, you get the derivative of the function and multiplied by the derivative of the function inside. So when we do this, we get f prime of x, 5 is our power, we multiply that in the front, we write down the function on the inside, we reduce the power by 1, and we multiply by the derivative of the function that's inside here. So 3 5s are 15 x squared minus 2, we get nothing from the 1, and that is our solution. We don't need to simplify, so we're done. The temperature of an oven is given by this formula, where C is the temperature in degrees Celsius and T is the time in minutes. Find the rate of change. So this rate of change, that basically tells us we have to work with a derivative. So we need to differentiate this function up the top. It's useful, I think, to rewrite the function by rewriting everything as a power. So a square root is a power of a half, and when it's in the denominator, it gets a negative sign. So this is t to the power of minus a half. And plus 5, square root is a power of a half, and then plus 15. That means we can just use the power rule directly on each of these terms and get the derivative. So we've got this function here. We just want the rate of change. So we just differentiate this. So negative a half times 30 is negative 30. Negative a half times 60 is negative 30. And then t, take 1 off, that's minus 1.5, which we'll write as minus 3 over 2. And then plus half of 5 is 5 over 2. And t, take off 1, minus a half. And we lose the 15. That goes to 0 when we differentiate. So that's our derivative. And we're interested in what the value of this derivative is when t is equal to 4. So minus 30, 4 to the power of minus 3 over 2, plus 5 over 2, 4 to the power of negative a half. These things here, so let's just on the side do 4 to the power of 3 over 2. Let's not worry about the negative sign for now. That's the same as 4 to the power of half and then cubed. A power of a power, you multiply these, so you can basically split this up. You could, if you wanted, split it up by doing the cubed first and then the half, which is the square root second. So this way, square root of 4 is 2, 2 cubed is 8. This way, 4 cubed is 64, square root of 64 is 8. Get the same 8. The negative means it's in the denominator, so we get here minus 30 over 8 plus 5 over 2. Square root of 4 is 2. The negative, it's in the denominator, so we can do a little bit of simplification. If we divide this by 2 and divide this by 2, we've now got two fractions with a 4 as the denominator, minus 15 here plus 5. So that's going to be minus 10 over 4, which simplifies to minus 5 over 2, and that's in degrees Celsius per minute. The negative sign tells us the temperature is decreasing. That's reassuring because that's what would happen when you turn the oven off. And that's our answer. Part C, what's the gradient of the normal to the curve y equals sine cubed x cos x at the point x equals pi over 4. Sine cubed x times cos x, yeah. That times in the middle here is important. So we should think of this as being times, and if when we say it out to ourselves or in our head when we're doing the problems, we remember that that's times, that will remind us that when we go to differentiate it, we've got a product, so we have to use the product rule. Stepping back a bit, what is the normal? Well, when you have a function, let's not worry about that function. Let's just say we've got y equals f of x, and we've got some picture of it. Looks like this. We've got a point. At the point, we'll have a gradient, and the normal is the line that's at right angles to our gradient. So our strategy here is we want to differentiate our function. We want to find the value of that derivative at the point that we're given, and this will be the gradient. Let's call it m for the gradient, which is often used, and then put a t, mt for tangent. And we're going to use the fact that the gradient of the tangent multiplied by the gradient of the perpendicular, the normal, is always equal to -1. And this is the key fact that's going to help us get a solution at the end. So we need to differentiate. We need to remember that it's a product, so we use the product rule. The product rule says write down one of the factors and multiply by the derivative of the other. Derivative of cosine x is minus sine x. And then add, differentiate the first one, 3 sine squared x. So remember that sine cubed x is basically shorthand for sine x all cubed. So this is a power function with a trig function inside. So you use the power rule and then the composite function rule, the chain rule. So we then have to differentiate sine. So we get multiplied by cosine x. And then we have to write down the second term. So it's multiplied by another cosine x. We can simplify this a bit. This is a negative sine to the power of 4x, and then plus 3 sine squared x cos squared x. And we want to evaluate this at the point pi over 4. So sine and cosine, pi over 4 is one of our special triangles. So if we have isosceles right angle triangle with sides 1 and 1, we get root 2. The angle here and up here, in fact, is pi over 4. Sine of pi over 4 is 1 over root 2. Cosine of pi over 4 is 1 over root 2. So sine pi over 4 equals cosine pi over 4 equals 1 over root 2. You can write that as root 2 over 2. It's not going to matter too much for us here which way we write it. I'm going to use 1 over root 2. So 1 over root 2, this is minus 1 over root 2 to the power of 4 plus 3 1 over root 2 squared times 1 over root 2 squared. So this is 1 over root 2 to the power of 4 as well. 1 over root 2 squared is a half, and to the power of 4 is going to be a quarter. So this is minus a quarter plus 3, and this here is a half times a half. times 3/4. So we're going to get minus 1/4 plus 3/4. It's going to be 1/2. That's the gradient of the tangent. We want the gradient of the normal, and that's going to be the negative reciprocal, because they multiply to -1. So if you change this, you get the gradient of the normal is -1 over the gradient of the tangent. So it's the negative and the reciprocal. So reciprocal of 1/2 is 2. The negative reciprocal is going to be -2. And that's our solution. I think they could have given us a little bit more room to do some working there. Got long expressions, maybe. Yeah, maybe you could do it. Well, yeah. You could save a little bit, but yeah. The graph below shows the function f of x equals x squared plus e to the power of 2x and the tangent to the curve when x equals 1. So we've got point 1 here. Find the point P. So we want to find this point P, the x-intercept of this tangent. To do that, we can use calculus. So we can find the gradient. At x equals 1. And then we can find a line through the point 1 and then f of 1, which we'll calculate in a minute, with gradient, and the gradient will be the derivative evaluated at 1. That will tell us the gradient at 1, won't it? So we can find a line through that point, and the line's going to have the form y minus f of 1 equals the gradient at 1 times x minus 1. And then along the x-axis, y is 0. So we then just put y equals 0 in here, and we've got an equation that we can solve and find x. So that's basically our strategy. Says here first to find the gradient, but we do need f of 1. So I'm gonna do that first. We need f of 1. That will tell us the y coordinate here. F of 1 is 1 squared plus e to the power of 2 times 1. That's just 1 plus e squared. You could calculate this out, but you don't need to, and you might get simplification later. So I like to leave any final calculation as late as possible in solving the problem. We want to find the derivative. So the derivative we get by differentiating this term here, this function here. X squared, we get 2x. Differentiating exponential, you get the same thing, but we've got a function inside 2x, so we have to multiply by the derivative of that. That's the chain rule. There's now a common factor of 2, so I'm going to write this as x plus e to the 2x. We need the value of this derivative when x equals 1. So we get 2 times 1 plus e squared. Yeah, we're just putting 1 in here, so we get 1 here, e to the power of 2 e squared. That's done. And now we want an equation of a line that goes through this point here, which is 1 and 1 plus e squared, and it's got this gradient. So our formula is, well, I've written it out here, but it's basically y minus y naught equals the gradient x minus x naught. We seem to have plenty of solution real estate here to write out things like this. So y minus, the function value is 1 plus e squared. equals the gradient, which is 2 times 1 plus e squared, and then multiplied by x minus 1. That's our point. We want to find what this is what happens when y equals 0, so we just leave off that last term, so we get minus 1 plus e squared equals 2, 1 plus e squared, x minus 1. Now this messy bit, we can just divide through by that. It's not 0, so that's a legitimate tactic. So we get now minus 1 equals 2x minus 2. Add the 2 on, so we get 2x equals 1. X is equal to a half. It said the point. You might want to choose to write the point as a half 0. They call it P. Yeah, you could say P. P equals a half 0. Part E, question 1. A curve is defined by the pair of parametric equations. So we've got two equations there. Find the coordinates of any points of inflection on this curve that are also stationary points. You may assume that any inflection point found are actually inflection points. You must use calculus and show any derivatives that you need to find when solving this problem. So this bit here, that you may assume that an inflection point found are actually inflection points, that's basically alluding to the fact that if we find the second derivative and we set it to 0, we will get some values. So x is in some set of solutions, and this thing is saying we can just assume that these are inflection points. In fact, just setting the second derivative to 0 doesn't guarantee an inflection point. You need to have the second derivative 0, and you need the concavity to change from positive to negative. So you need to be going like this, and then like this. You get a point of inflection here, or like this, and then like this. The slope at the point of inflection doesn't have to be on the side, and this question here actually says we want ones that are stationary points. That's a bit like this could be y equals x cubed. It's got a point of inflection at the origin here. So we don't have to actually determine that. We can just assume that we've got a point of inflection. So as alluded to here, we want the second derivative, but to get the second derivative, we need the first derivative, which will also help us find the stationary point. So we need dy by dx. And with parametric equations, the way you get dy to bx is by differentiating with respect to t, and then multiplying by dt dx, or this is effectively dividing by dx by dt. So in practice, then divide by dx by dt. So we need to find these two things here, dy by dt. We differentiate this. It's a power, so it's 3 times 2 is 6 t squared, and we need to find dx by dt. That's a polynomial, so 2 3s are 6 t, and then plus 6. Probably useful to write that in a factorized form by taking a factor of 6 out. And now we have dy by dx, which is 6t squared, dy by dt, divided by 6 times t plus 1. The 6's cancel, so we've got t squared over t plus 1. There's our first derivative. We want stationary points, so that has to be 0. And a fraction is 0 only if the numerator is 0. T squared equals 0. We just get the one solution, t equals 0. You might want to note t can't be -1 because we're dividing by this, but that's not going to affect our stationary point because -1 isn't a solution there. So we've got stationary point at t equals 0. And we want to find now the second derivative to find where there are points of inflection. The way to do a second derivative with parametric equations is to differentiate with respect to t the first derivative and then multiply again by dt by dx, or divide by dx by dt. So that means we need to differentiate this thing here. It's a quotient, so we're going to need to use the quotient rule. Some people like to write down u equals t squared, the numerator, and u primed is therefore 2t, and v equals t plus 1, and v primed is equal to therefore 1. You can do the whole thing, and then you can do the whole thing without doing that. So the derivative of a quotient, so u over v, if you differentiate that, you get v times u primed minus u times v primed over v squared. I prefer with something that's got relatively simple functions that I can differentiate in one step, for example, just to do this directly. So the quotient rule says write down what's on the bottom and multiply that by the derivative of what's on the top, and then subtract off, write down what's on the top and multiply by the derivative of what's on the bottom, and then divide by the denominator squared. Then we have to multiply by dt by dx. So dx by dt was this, so we've got to times 1 over 6t plus 1. No, that's the derivative. Oh yeah, sorry, misread what I've written, or where I've written it. So that's our second derivative, and we want that to be 0 in order to have a point of inflection. We've got the same problem with t plus 1. We're going to have t plus 1 cubed when we put these together, so we can't have t equal to negative 1. So I should have written not equal to here. Otherwise, to solve this, we just need the numerator to be 0. You could tidy it up first, but we can go directly to, therefore, t plus 1 times 2t, so that's 2t. Well, actually, I think you can do better than that. We can see that the numerator has got a common factor of t, so we can take that common factor out. So it's t times 2t plus 2, and then minus, there's going to be 1t here, has to be 0. Actually, as soon as we've got a t out here and multiplied by something, we can see that that implies that t equals 0, and that's going to be our point, because that's where there is a stationary point. But if you weren't sure, you could carry on. 2t minus t is t plus 2 equals 0. That implies t equals 0, or t equals negative 2. This one's no good to us because it's not a stationary point. It will be a point of inflection. Well, we can assume it is. So point of inflection that is a stationary point when t equals 0, that is x equal to 3t squared plus 6t plus 1, 3 0 squared plus 6 0 plus 1, which equals 1, and y equal to 3t cubed, 2t cubed. 2 times 0 cubed, which equals 0. So this is our point. Move on to question 2. Differentiate. You do not need to simplify your answer. Very similar to question 1. We've got slightly more complicated functions. As I say, with any x type term here in the x power of x term in the numerator or the denominator, I prefer to rewrite this out as a power, so I would write it as 7x to the power of minus 1 minus the logarithm 3x cubed minus 2x squared plus 5, and then do the differentiation from there. And not needing to simplify, you shouldn't really need more than one line to do this. A power function, multiply by the power, 2 lines, I suppose, if you write that out. So minus 1 times 7 is negative 7, and it's going to be x to the power of minus 2. And then minus, when you differentiate a logarithm, you get the reciprocal. And because this logarithm has a function inside, it's a polynomial this time, but it could be any function, we have to differentiate what's inside. So 3 3s are 9, x squared, 2 2s are 4, x, and the 5, oh, I didn't mean to write square bits around there. I meant to write a bracket. And you do not need to simplify your answer. This should be enough. You could rewrite this bit here as minus 7 over x squared. You could write this with the 2 bits over. If you had to do some working with it, you'd get a common denominator, etc. But this is not needed. We're explicitly told we don't need to simplify. So just testing the differentiation techniques. Power rule, how to differentiate logarithm, chain rule. Part B, the depth of water in meters in a particular harbour is given by the formula P equals 30t minus 5t squared, all of that times e to the power of minus t, where t is measured in hours and 0 is less than t less than 4. Show whether the depth of the water in the harbour is increasing or decreasing after 2 hours. So increasing, that means the derivative, our function is called P, our derivative has to be bigger than 0, and decreasing, this means the derivative would be less than 0. So effectively we've got to calculate this derivative. We're interested in the point when t is 2 hours, and we want to see whether we've got something that's increasing or decreasing. So it's a product, 30t minus 5t squared, all of that times e to the power of minus t, so it tells us a product, so we use the product rule. The derivative of p is equal to, write down one of these, differentiate the other. So differentiate e to the minus t, you get e to the minus t. It's got a function inside, a simple function, minus t, so you have to then multiply by minus 1, the derivative of what's inside. And then plus, differentiate the other one, so that's 30 minus 10t, and then write down the other factor. Immediately you can see you've got a common factor of e to the minus t, so I think it's useful to put that out the front and then multiply this by, it's the negative of this, so that's going to be 5t squared minus 30t, and then over here it's plus minus 10t, so it's minus 10t and then plus 30. You could simplify, you could tidy this up, minus 40t, but the the key thing is we're only interested in whether this is increasing or decreasing. You put the whole thing, just put t in. You could put t equals 2 into your calculator and get a solution. However, it's simpler than that. It's a known fact that e to the minus t is bigger than 0 always. So that means we've got a positive number out the front, and this will be positive. The whole thing will be positive depending on whether this is positive or negative. So we can just investigate 5 times 2 squared minus 40 times 2, and then plus 30. 4 5s are 20, minus 80, plus 30. And you can work it out, but it's less than 0, therefore decreasing. At t equals 2 hours. Question C. There are two tangents to the curve y equals f of x equals x squared over x plus 4 that have the equation y equals minus 3x plus c. Find the coordinates of the 2 points of contact of these tangents with the curve y equals f of x. So minus 3x, that's going to be, goes down 3, across 1, up 3. So we're getting a line like this, it looks like. There's one solution over here somewhere, and there'll be one solution down here. So I'm just going across 1, up 3. So I'm want to get a line that's parallel to something like this. It's just a rough estimate. It's telling us basically where I'm going to expect to find these solutions. This here tells us the gradient is -3 of the tangent, so the gradient of the function. So we have to differentiate this and find where the gradient is -3. That's going to be our strategy. So we've got a quotient, so we need to use the quotient rule. As I said, people like to write u equals x squared, not another equals. U primed is therefore 2x. V is equal to x plus 4, and v prime will be 1. You can do all that. I prefer just to dive straight in when the derivatives are simple things that we can do in our head. Write down the denominator. That's v, multiply by the derivative of the numerator, 2x. Take off, write down the numerator, multiply by the derivative of the denominator, and divide all of that by the denominator squared. And we want this to be -3. I can see straight away, and I think you should be able to too, that you're going to get a quadratic out of this. So when you multiply it up here, we're going to get an x squared term here, and there's some x squared terms in here, and so we get a quadratic that we're going to have to solve. So x, let's just expand everything out and multiply this over the other side. So therefore 2x squared plus 8x minus x squared has to equal -3 times x squared plus 8x plus 16. And if we're being very careful, we want to say that x can't be -4, because that's we don't have anything there, but x is -4 is this asymptote down here. So from our sketch, it doesn't look like that's going to bother us. So we now get 2x squared. We've got -3x squared here, so that's going to be 5x squared over this side. We've got 8x, and we've got -24, so that's 8 and 24, so plus 32x. 2 plus 3 minus 1, so this is actually 4x squared. No constant terms here, and we've got minus 48, so we're going to get plus 48 over here, equal to 0. These have all got a factor of 4, so we can divide by 4. And two numbers that multiply to 12 add to 8. That's 2 and 6. 2 6s are 12, 2 plus 6 is 8. So x is negative 2, or x is negative 6. And I think that's all. I didn't say coordinates. Find the coordinates of the 2 points. So we need to, at both of these points, we need to find out the function value. What's it called? F? Yep. F of negative 2 is equal to negative 2 squared over negative 2 plus 4. Is that right? Negative 2 plus 4. Negative 2 squared is 4 over 2, so that's 2. And f of negative 6 is negative 6 squared over negative 6 plus 4. This is 36 over negative 2, so that's negative 18. Yeah, plus 2 looks like, so it's at 2, it's right at this point here. And negative 6 it's actually this point over here. So a little bit out, and that looks like it's down at negative 18. So the coordinates are negative 2, 2, and negative 6, negative 18. Find the equation of the tangent to the graph defined by the pair of equations y equals 2 sec t and y equals 5 tan t at the point on the graph where t equals pi over 6. You must use calculus and any derivative. So we've got a parametric equation. We want the equation of a tangent. So that to find the equation of a tangent, we need to find the gradient, which we find by differentiating. So we need dy by dx, which for parametric equations, as we've already seen, is dy by dt times dt by dx. We need to find those things. So dy by dt, differentiate tan, you get sec squared, and differentiate sec, you get sec tan. So dy by dx is equal to 5 sec squared t over 2 sec t tan t. The sec t cancels with one of the sec t's on the top, so we've got 5 sec t over 2 tan t. Now we could simplify that. Sec is 1 over cosine, and tan is sine over cosine. Effectively, the cosines will cancel, so you could, and then we'd have 1 over sine. So we'd have, you could write this as 5 over 2 cosec t, I think, or 1 over sine, whatever is useful for you. Find the equation. So to find the equation, we need the point on the graph. So we need the x and y coordinates. So x is equal to 2 sec pi over 6, and y is equal to 5 tan pi over 6. Pi over 6 is one of our angles and one of our special triangles. If we have 1, 2 here, this is half of an equilateral triangle. We get root 3 up here. This is the angle pi over 6, 30 degrees, if you like. So we've got sec, which is 1 over cosine. Cosine pi over 6 is 3 over 2, root 3 over 2. So sec pi over 6 is 2 over root 3. Tan pi over 6 is opposite over adjacent, 1 over root 3. We could do that in here, cosec if you like. Well, yeah, well, this is something you could do, but we can do all the calculations with sec and tan from here. So we get 2 sec pi over 6 is times 2 over root 3. So that's 4 over root 3. And here we have, this is equal to 5 tan, tan is what we've just calculated, 1 over root 3. So this is 5 over root 3. That's our point. We want an equation of a line that goes through that point, and we want dy by dx as well, evaluated at pi over 6. So we just put those into here. So that's 5 sec is 2 over root 3, all divided by 2 tan, which is 1 over root 3. We get a lot of cancellation here. The root 3's on the bottom cancel, the 2's cancel. So I think this is just 5. So we want an equation that goes through this point, x, y coordinates, and with this gradient. So it's y minus 5 over root 3 equals 5 times x minus 4 over root 3. Find the equation of the tangent to the graph by the pair of equations. You could leave that like it is, but more standard would be to various standard forms we can write it in. So we can write this as 5x minus 20 over root 3, and then plus 5 over root 3. So y equals 5x minus 15 over root 3 would do. Maybe you don't like square roots in the bottom, so we could multiply this by root 3 over root 3. We get minus 15 root 3 over root 3. Squared now, so you've got no root over 3. That cancels to 5. So you could write that as 5 times x minus root 3. And various other forms you could write the equation in. The radius of curvature of a function is a measure of how much the curve is bending at a given point. The formula to calculate the radius of curvature is given by P equals this mess here. Find the radius of curvature for the curve y equals cosine squared 2x when x equals pi over 3. So what do we need? We need, this here's a second derivative, this here's a first derivative. So we need to calculate the first and second derivatives of this function and then just throw them into this messy formula and hopefully get a sensible answer out. So dy by dx is a squared of a trig function, and then there's a function inside, so it becomes 2 cosine 2x to the power of 1, and then multiplied by the derivative of what's inside, so multiplied by 2, that's 4 cosine 2x. That's the first derivative. Okay, these derivatives look straightforward. Second derivative, we have to differentiate this, so it's just, no, I made a mistake. I made a big mistake. There are 2 bits inside, aren't there? 2 cosine to the power of 1 cos 2x. Now we have to differentiate the cosine. Differentiate cosine, you get minus sine 2x. and then repeated application of the chain rule, we have to differentiate what's inside here, so we get 2. So this is actually 4, negative 4, cos 2x, sine 2x. Now when we differentiate the second time, this is a product, so we have to use the product rule. So it's minus 4, write down the first, differentiate the second, so that's cosine 2x, and then multiply by 2, and then plus, let's differentiate the cosine, so it's minus 4 times minus sine 2x times 2, and then write down the second one. So we've got 4 2's 8 with a minus sign. We've got 4 2's 8 with 2 minus signs. So it's going to be, there's going to be a common factor of 8. This one's going to be plus, so it's going to be sine squared 2x, and then minus cosine squared 2x. So we want these at x equals pi over 3. Pi over 3 is again the same special triangle we had before. This angle here, though, now is pi over 3. Oh well, actually we should get twice that, so we get 2 pi over 3. That's all right. We can work that out. Yeah. So let's sine pi over 3 is root 3 over 2. Cosine pi over 3 is 1 over 2. We, however, want 2 pi over 3. This is sine. Pi over 3 is here somewhere. 2 pi over 3 is here. It's the sine of pi over 3 equals the sine of 2 pi over 3. If you're unsure, you can do that on your calculator. And similarly for cosine, pi over 2, yeah. So pi over 3 is here somewhere. 2 pi over 3 is here. The cosine of 2 pi over 3 is equal to the negative of the cosine of pi over 3, which is equal to negative 1/2. So we've got all the things we need to do this calculation. So let's dy by dx evaluated at pi over 3. It's this thing here, so it's minus 4 cos 2 pi over 3 is negative 1/2. Sine 2 pi over 3 is root 3 over 2. So the 2's on the bottom cancel with the 4, the negatives cancel, so this is just root 3. The second derivative evaluated at this point is 8 times sine squared. Sine is the same as, so it's root 3 over 2 squared, and then minus the cosine squared, which was negative 1/2 squared. That's 8 times 3 over 4 minus 1 over 4. So that's 1/2 of 8. Looks like it's going to be 4. So we've got a root 3 that goes in here, and we've got a 4 that goes in the bottom. So we get P, the curvature, 1 plus root 3 squared to the power of 3 over 2, all divided by 4. I think that's right. Root 3 squared is 3, 1 plus 3 is 4, so this is 4 to the power of 3 over 2 divided by 4. This is 4 to the power of 1, so subtract, so it's 4 to the power of a half, so it's 2. Question 3. The graph below shows the function y equals f of x. For the function above, find the values of x where f of x is not differentiable. So it's not differentiable when we've got holes. So we've got or jumps. So we've got a jump here. So it's not differentiable if x is in the set -6. We've got a hole here and a point up here, so it's -2. You can't differentiate it. Here you can't differentiate it, got a hole, but even if it wasn't a hole, it would be a sharp corner, which is not differentiable. And I think that's the only 3 values. Find the values of x where the derivative equals 0. Well, it's equal to 0 all the way along here, so it's x less than -6. It'd be wrong to put less than or equal to, because equal to is a non-differential point. It's equal to 0 as well at this turning point, so that looks like x equals 4, -4, and it's equal to 0 at this turning point, so x equals 6. Everywhere else it's positive or negative or undefined. What is the value of the limit as x goes to -2 of f of x? X goes to -2, so we're coming along here towards -2, or coming along here towards -2, and when we go along the function in both directions, are we getting to the same point? Yes, we are. We're getting to this point here, so this point is the limit. It's irrelevant that the function value is up here. We're looking, the limit is saying, as we go along the function, as we get closer and closer to 2 from both directions, are we getting to an actual value? So the limit as x goes to -2 of f of x is equal to 2. B. A curve has an equation y equals log x over 2x. Find the x coordinates of any stationary points on the curve. Need to find when solving this problem. So let's just differentiate. It's a quotient, so u is log x. The derivative of u is therefore 1 over x, and v is 2x, and the derivative of v is therefore 2. So we write down the denominator, 2x, multiply by the derivative of the numerator, 1 over x, minus, write down the numerator and multiply by the derivative of the denominator, divided by the denominator, all squared. We want this to be 0 for a stationary point. We can't have the numerator 0, so we probably should note that x is not equal to 0. That means that the numerator has to be 0, so 2x times 1 over x is just 2 minus 2 log x has to be 0. So 2 log x has to equal 2, log x has to equal 1. Take exponentials, x is equal to e to the power 1, which is e. find the x coordinates. That's done. I think we would technically need to show that this any stationary point. No, it doesn't say. We don't have to find out what sort of stationary point it is. Here, the derivative is 0. This is a stationary point. So that's done. A solid spherical lump of ice is melting while maintaining its spherical shape. At the instant when the radius is 6 centimeters, the radius of the ball of ice is decreasing by 0.05 centimeters per second. Find the rate at which the volume of the spherical ice ball is decreasing at the instance where the radius is 6 centimeters. So V, the volume of a sphere, is 4/3 pi cubed. We know something about dr dt. That is 0.05. It's a negative. It's decreasing centimeters per second. The question says find the rate at which the volume of the sphere of ice. So we want to find this. dv dt is going to be dv dr, and then multiplied by dr dt. So what we need to do is we need to differentiate the volume with respect to r. So 3 times this will give us, the 3's will cancel, so you get 4 pi r squared, and times dr dt. So yeah, we'll just leave that as dr dt. We're going to substitute this in, but this is dr dt at specifically r equals 6. So when we put r equals 6 in here, then we can legitimately put this value in. So it's 4 pi times 6 squared times negative 0.05. 6 squared is 36. 4 of those is 144, and this is 1/20th. So negative 144 over 20 pi. We can always divide by 4. 4 3s are 12. 4 6s. So negative 36 over 5 pi centimeters cubed per second. You can work that out. Use a calculator if you want. I think leaving it with a pi and that should be okay. Pi is an accurate, exact number. If you put it into a calculator, you'll just get a rounded solution, unless you keep the pi's anyway. The equation of a curve is given by the pair of parametric equations. Wow, lots of parametric equations in this exam. Find the coordinates of the points on the curve where the gradient is negative 2. Okay, so we've looked at these, so we want to just find the gradient. So the gradient dy dx, remember, it's dy dt times dt dx. So we need to find dy dt. That's an exponential, so it's just going to be 5, the same exponential, and then multiplied by 2. And dx dt, that's also an exponential. So actually I think it's helpful to write x as 5e to the minus 2t. So it's 5e to the minus 2t, and then multiplied by negative 2. I suppose you can write this as 10e to the 2t, and you could write this one as negative 10. I'll leave it as a negative power. Find the coordinates of the point on the curve where the gradient is negative 2. So we haven't quite got to the gradient. Dy dx is this one, 10e to the 2t over negative 10e to the minus 2t. And now these simplify, so we get a negative sign. 2t minus 2t, that's e to the 40. That appears to be our gradient. and we want to know when this gradient is equal to -2. So therefore, we need e to the 4t equal to 2. Take logarithms, we need 4t equal to the logarithm of 2. T is equal to the logarithm of 2 divided by 4. Now that's our t value. It says to find the coordinates of the points. There's only one of them, it seems, so x is equal to 5e to the minus 2 times the logarithm 2 over 4. That's 5e to the, this is a half, isn't it? Minus a half logarithm of 2. Can put that in here, so it's 5. A number out the front of a logarithm is makes it a power, so 5e to the logarithm 2 to the minus half. E and logarithm cancel, so this is just 5 times minus means it's on the bottom, half means it's a square root, and y is equal to 5e to the 2 logarithm 2 over 4. So this is 5e to the logarithm 2 to the power of a half. So this is just root 2, so this is 5 root 2. So it looks like our point is 5 over root 2, 5 root 2. If you wanted, you could get rid of the, rationalize this denominator, so you get 5 root 2 over 2, 5 root 2. The diagram below shows a part of the symmetrical graph y squared equals x 16x minus x squared. That's a circle. A rectangle ABCD is drawn inside the curve with its vertices B and C lying on the curve. Find the length AD so that the rectangle has its maximum area. So if we made this point here have a coordinate x, and then the height is the y value, which is given by y equals the square root of 16x minus x squared. It's symmetrical. This point here is going to be when x equals 16. So we can factorize here to say this is x times 16 minus x. And we can see that the zeros are at 0 over here and 16. So the coordinate of D is going to be 16 minus x. So we've got a rectangle with height root 16x minus x squared and width 16 minus x and then minus another x. So 16 minus 2x is going to be the distance from here to here, 16 minus 2x. So it's got area. Therefore, the area is 16 minus 2x times the square root of 16x minus x squared. Let's just call that A equal to the area. Now we want to find the maximum area. So that is, to do that we find a derivative. This is a product, so write down 1. differentiate the other. This is a power of a half, so it becomes a half. That to the power of minus a half times the derivative of what's inside, 16 minus 2x. And then plus, differentiate this one, minus 2, and write down the other one. Don't need a parentheses, 16x minus x squared. And to get a maximum, we want this to be 0. (16 minus 2x), this times the derivative of this. Yeah. Yeah, so let's just rewrite that. So we've got 16 minus 2x. We seem to have that twice. So it's squared over 2 root 16x minus x squared. And then it's going to be a minus 2 root 16 minus x, 16x minus x squared. And we want that to be 0. We effectively can put this on the same denominator by multiplying this by 2 over 16x minus x squared. So we get, this is the same as 16 minus 2x squared minus 4 times 16x minus x squared over, it really implies 2 root 16x minus x squared equal to 0. We're going to need the numerator to be 0, so we can, I think, multiply this out. So we need, therefore, we need 16 squared is 256, 32 minus 64x plus 4x squared. It's plus another 4x squared and minus 64x equal to 0, so that's 8x squared minus 128x plus 256 to 0. Can divide by 8. 8 goes into here once, and 16. 8 goes into here 3 times 32, so we get x squared minus 16x plus 32 equals 0. That looks nice to solve by completing the square. Halve this, you get 8 squared is plus 64. That's where to add 32 on. That. So this is x minus 8 all squared is equal to 32. Take the square root. X minus 8 is plus or minus the square root of 32. X equals 8 plus or minus the square root of 32. 32 is 16, so 16 times 2, so that's 8 plus or minus the square root of 16 times 2. 8 plus or minus 4 root 2. And I think those two values are basically going to give us x as either end of this, because if we make x big, 16 minus x is going to be small. It's just flipping these around. So you must use calculus to show that. So we want to find the length AD. So we want 16 minus 2x. That's our length AD, which is 16 minus Yeah, actually, well, I think we want the difference between these two roots. So we want 8 plus 4 root 2 minus 8 minus 4 root 2, which is going to give us 8 root 2. Yep. AD is equal to 8 root 2. I think that's the solution. Do you get that when you do 16 minus 2x? So 16 minus 2 times 8 plus 4 root 2. 16 minus 16. Yeah, that's right. 16 minus 16, that cancels. So you get minus 8 root 2, and it's negative because we've done the subtraction the wrong way, basically. So 16 minus 2 times 8 minus 4 root 2. Oops, not a very good root. That's what I couldn't see before. Now that was going to work. 16 minus 8, 2 8s are 16. And then minus minus, this is going to be 8 root 2, which is the same as what we got over here. So this one here is got a negative sign just because we're starting with the small one and taking off the big. If we use the big root, then the a and the d swap around and you get a negative sign. So otherwise, this is good. Any questions? Let me know, and we will see you again next time.